Hello, welcome to this week's lecture on soft in, soft out decoding. We're going to proceed with looking at soft in, soft out decoding for single parity check codes. Once again, I'll take a simple example and I will generalize from that later on. Okay. So, what is the single parity check code? Okay. So, it is an n comma n minus 1 linear block code. Okay. And the way it works is as follows. If it's n comma n minus 1, remember this is k, right? K is n minus 1. So, your message vector is m1, m2, mn minus 1. In most cases, it's encoded in a systematic fashion. This is how the encoder works. Okay. Your code word is going to be the same message bits appearing in the first n minus 1 positions, and in the last position you will get a parity bit, and this parity bit is simply the XOR of all the previous message bits, all the message bits. Okay, so this is the message, this is the parity bit. So you can see why this is called the single parity check code. You have how many ever message bits you want, you just put out one parity, which is the XOR of all the message bits that have been seen so far. Okay, so let's look at the 3,2 single parity check code, SPC code. I will abbreviate this as SPC code. Okay, so here the message could be 00, 01, 10, 11, and what will the corresponding code word be? 00, and the parity here is going to be 0 again. The XOR of these two is 0, 01 you will have 1, 10 you have 1, 11 you will have 0. Okay. So, there are quite a few things to notice here. For instance, the number of ones in C is always even. Okay. So, the single parity check code consists of all the even weight vectors of length n. Okay. Okay, the SPC code consists of all even weight vectors of length n. Okay, so this is quite easy to see. So, the single parity check code is described in that fashion. Now, what about generator matrix, parity check matrix for single parity check code? The generator matrix is quite easy to write down. You have I n minus 1. Okay. So, once you are done with the I n minus 1, the parity check part has only a single column, and that is just all ones. All ones. It is called n minus 1, n here. Okay, n minus 1. And then you have all ones coming up. Let me write the one in a distinguished way. You have all ones coming up on the right side. Is that okay? So, the identity part is the systematic part, and then you have sort of a division here, and then you have the P part, which is just all ones. Now, if you convert this into a parity check matrix, the parity check matrix, if you remember from the dimension, is just 1 cross n. It is basically one row, all ones. Okay, this is just all ones in a row. Okay, so this is quite easy to see why this is true. The only parity check that you have is C1 XOR C2 XOR C3 XOR so on till Cn equals 0. Okay. So, this is a characteristic of the single parity check code. So, if you take a code word of the single parity check code, you XOR all the bits together, you are going to get 0. Okay. So, this is the single parity check code. I showed you a small example. Larger examples will give you many more code words. So, for instance, if you look at the 10,9 single parity check code, you will have 512 code words, 2 power 9 code words, which are all even weight and of length 10. Okay. So, that is the description of the single parity check code. Okay. So, it looks quite complex, but it turns out even for this code you can do a very simple SISO decoder. Well, simple as in, you will see eventually the description will become simple, but it is something very interesting. You can do a very nice and simple implementation for the SISO decoder. Okay, so that will be our focus in this lecture. Okay, so I'll take the 3,2 code as an example and show it, and then we will generalize later on. Okay, so how is the 3,2 code working? You have the message vector being M1, M2. Sorry. Okay, so this goes into the SPC code encoder, and you produce a code word which is C1, C2, C3. Now, this will go into BPSK, and then Gaussian noise, and then you get your received vector, which is R1, R2, R3. Now, what do I want to do with this? I want to build a SISO decoder. Remember, what do I want to produce here? My capital L1, capital L2, capital L3. Okay, believes about the 3 bits C1, C2 and C3. Okay, so this is something interesting. One can look at what the single parity check code means and all that. I'll talk about it as we derive this. Okay, so to think about this, let's look at L1. How do we compute L1? L1 is going to have an intrinsic part, which is just R1. It's going to be proportional to R1. Okay, we know that. And what about the extrinsic? So to answer this, look at what that question really means. What do R2 and R3 say about C1, right? So that's the question about the extrinsic information, right? So this was R1 was quite easy. What does R1 say about C1? It's just proportional to that. We saw that in the channel LLR calculation. Now for the extrinsic part, what do R2 and R3 tell about C1? Okay, R2 says something intrinsic about C2. Likewise, R3 also says something intrinsic about C3, but what do C2 and C3 tell about C1? Okay, C1 equals C2 XOR C3. Okay, so this comes from the parity check condition. Okay, so this is the route we have to take. Okay, R2 says something intrinsic about C2, R3 says something intrinsic about C3, and I know C1 is C2 XOR C3. Okay, so now I take the intrinsic information from R2, take the intrinsic information from R3 into C2 and C3, and then use this XOR to compute what it says about C1, and that will be the extrinsic information for C1. And then I add intrinsic and extrinsic, I get my total capital L1. Is that okay? So that's the strategy we're going to take, and it turns out this is not too bad a computation. You can do it without too much trouble. So let me show it in a slightly different way here. So I have C1 equals C2 XOR C3. Okay, and somebody tells me that L2, right, is the log of probability of C2 equals 0 given R2 divided by probability of C2 equals 1 given R2, and then L3 is log of probability of C3 equals 0 given R3 divided by probability of C3 equals 1 given R3, right. So this is given to me. From here one can go to this, so maybe I'll call this guy as P2, I'll call this guy as P3 just for simplicity. Okay, so remember, once I call that as P2, this is actually 1 minus P2. Okay, so this also denominator is 1 minus P3. Okay, so this is just probability of 0 or 1. One needs both of them have to add together to give you 1. So this is the same thing. Okay. So there are various ways to do this changing around. So, L2 is log P2 by 1 minus P2, right. So, from here you can find out P2 as well. So, you can write down what P2 will be in terms of L2 and all that. We will come to that a little bit later, but just remember this this conversion. Okay. So, given P2 and P3, what is P1? Okay. So, that's the extrinsic. Okay. So, how do I compute P1? So, what is the probability? So, given these two P2 and P3, what is probability of C1 equals 0, let us say given R2, R3. Okay, so, that is the main question here. So, if I can crack this, if I can figure out from P2, P3 what this probability of C1 equals 0 will be, I would be done. Okay. So, now what is, so remember the R2 and R3 for a particular code word are independent, otherwise they are not. So, it needs to be a little bit careful in this computation, but I'm not going to go through it so rigorously. I'll just motivate it and give you the final answer in a reasonable way. Okay. So, if you look at the cases when C1, C2, C3, C1 is 0 if C2 and C3 are 0 and C2 and C3 are 1. And C1 is 1 if C1 and C2 are 0, 1 or 1, 0. Okay. So, this is how C2 and C3 decide what C1 will be. I'm given only C2 and C3. I want to figure out what C1 is. This is how it works. Okay. So, if you want to look at P1, okay, which is probability of C1 equals 0. So, maybe I should call this as P1. Okay. This is going to be, right, P2 times P3, okay, that is the first term here, plus 1 minus P2 times 1 minus P3. Okay. That is the second term here. Okay. So, how do I know what C1 is? C1 is 0, C2 is 0, C3 is 0, that is P2 times P3. C2 is 1, C3 is 1, which is 1 minus P2 times 1 minus P3. The same way you can also write 1 minus P1, which is the probability of C1 is 1, and that will be P2 into 1 minus P3 plus 1 minus P2 into P3. Okay. This is nice. Okay, seems decent enough. Okay. So, the most interesting thing, so now of course you can start working with this and see what you can derive, etc. So, it turns out there is a way to slightly simplify this computation. So, for that one needs to look at P1 minus 1 minus P1. Okay. So, I am going to subtract these two, and when you subtract these two, you will see what will happen is you will get this product. Okay. So, you will get P2 times P3 minus 1 minus P3 plus 1 minus P2 times 1 minus P3 minus P3, right. So, you can take things common here and you will get P2 minus 1 minus P2 times P3 minus 1 minus P3. It is a simple little observation, but this will help us simplify a lot of things. Okay. P1 minus 1 minus P1 equals P2 minus 1 minus P2 times P3 minus 1 minus P3. Okay. So, sounds simple enough, but it's nice to do. Okay. So, what people do, see, remember I want to go from L2 and L3 to L1. Okay. So, that is what the extrinsic, or not to L1, L2 and L3 to the extrinsic information about P1. So, actually what I am interested in, I am interested in the computation of log P1 by 1 minus P1. Okay. So, this is the extrinsic information, extrinsic LLR, right. So, I need to compute this guy. Okay. So, how do I compute this? It turns out you can divide throughout by this guy, basically divide throughout by 1 and write 1 as different things here. This is allowed, it is all just 1, I am writing it in a different way. So, now I can divide by P1, okay, divide this ratio by on the left hand side by P1, this ratio by P2, this ratio by P3. So, you will get here 1 minus P1 by P1 by 1 plus 1 minus P1 by P1. These are all just algebraic tricks, but nevertheless it plays an important role in the implementation. You will see how it works. 1 plus 1 minus P2 by P2, 1 minus 1 minus P3 by P3 by 1 plus 1 minus P3 by P3. Okay. Okay, so this is the expression I have. Now remember, I am interested in the extrinsic LLR, okay, log P1 by 1 minus P1. Okay, so I am going to define this as Lxt1, which is log P1 by 1 minus P1. This is the extrinsic LLR about bit 1. I am interested in this. Okay, so let's write everything in terms of the extrinsic LLR and L2 and L3. Okay, so how do I write that? So if you notice here, this is 1 minus e power minus Lxt1. Why do I get the minus? It's because the ratio is inverted. You will get the minus here. 1 plus e power minus Lxt1. Okay. So likewise here you will have e power minus L2 by 1 plus e power minus L2 times 1 minus e power minus L3 by 1 plus e power minus L3. Okay. So once again, I will remind you about the tan hyperbolic function. It's e power x minus e power minus x by e power x plus e power minus x. In fact, one can write this as 1 minus e power minus 2x by 1 plus e power minus 2x. Okay, so it's the same thing. So once you notice that, you will see that this product is just the tan hyperbolic of Lxt1 by 2 equals tan hyperbolic of L2 by 2 times tan hyperbolic of L3 by 2. Okay, so this is a very famous formula for XORs. So if you have C1 equals C2 XOR C3, it results in this tan H rule. Okay, so you can call it the tan H rule. You remember in the repetition code, when C1 and C2 and C3 were the same, the extrinsic was simply Lxt1 equals L2 plus L3. Okay, you just added the two. Okay, in the repetition code, you add the other incoming LLRs to get extrinsic. Okay, in the SPC code, single parity check code, when you have C1 equals C2 XOR C3, given L2 and L3, what is Lxt1? You have to use the tan hyperbolic rule. Tan hyperbolic of Lxt1 by 2 equals tan hyperbolic of L2 by 2 times tan hyperbolic of L3 by 2. Okay, it looks a little complicated, but one can do this with some plots. In fact, what people usually do is the following simplification. Okay, so tan hyperbolic is an odd function. Okay, and also if x is negative, tan hyperbolic is less than 0. If x is positive, tan hyperbolic is greater than 0. Okay, so the sign of x and the sign of tan hyperbolic of x is exactly the same. Okay, so this equation involving tan hyperbolic can be written in two different ways. One is sine of Lxt1 equals sine of L2 times the sine of L3. This is just the signs. Okay, and then absolute value. Okay, so you can take the absolute value separately and you will get tan hyperbolic of absolute value of Lxt1 divided by 2 equals tan hyperbolic of absolute value of L2 divided by 2 times tan hyperbolic of absolute value of L3 divided by 2. Okay, so what is nice about dealing with absolute value and positive things? Product can become addition by taking log. Okay, once everything is positive, I can take log. When I take log, everything becomes a bit different. So let's look at this. Log tan hyperbolic of absolute value of Lxt1 by 2 equals log tan hyperbolic of absolute value of L2 by 2 plus log tan hyperbolic absolute value of L3 by 2. Okay, so that's a nice enough formula here. I'm not doing any multiplication, I'm just adding. So at this point, we're going to define a function f which conveniently captures this log tan hyperbolic. So you see this log tan hyperbolic of the quantity by 2 is occurring again and again. So it's good to define a function f which captures this this log tan hyperbolic. So let's do that. For x greater than 0, we're going to define f of x as absolute value of log tan hyperbolic of absolute value of x by 2. Okay, so this is the definition. So if you look at it closely, tan hyperbolic of absolute value of x by 2 sort of captures this, and if you take log, you will get log, that's fine, but it turns out
that this log actually, so tan hyperbolic will be a value between 0 and 1. So, if you take log, you will get something negative. Okay. So, I do not want the negative part there, I just want the absolute value. So, I put absolute value here. Okay. So, that is how it works. And one curious fact about this function is f inverse of x is actually the same as f of x. Okay. So, this is the function here, and this is important. Okay. So, once we have this function, we can conveniently express this result in terms of its absolute value and its sign in a very easy manner. Okay.
This equality is f of Lx1 absolute value equals f of L2 plus f of L3, right. Okay. So, now how do I invert this? Take f on both sides, we will simply get absolute value of Lx1 equals f of absolute value of L2 plus f of absolute value of L3. Okay. So, this is another way to write down the tan H rule. This and sine of Lx1 equals sine of L2 times sine of L3. Okay. So, this was the derivation for the soft input soft output decoder for single parity check code. So, now let me summarize. This is a bit of a long derivation, and I think so the derivation is slightly important to know where these things come from, but finally the implementation is equally important. Let me tell you where all of these get finally implemented as. So, when you want to build the SISO decoder for the SPC code, what is going to be your capital L1, capital L2, capital L3. Okay. So, you have the intrinsic, which is L1, L2, L3, and you have the extrinsic, which is Lx1, Lx2, Lx3, okay, and your capital Li is small li plus Lx I, okay, just the addition of these two. How do I find Lx1? You use this formula here. How do I find Lx2? Okay, so it's not very hard. You simply use the same formula as before, except that you use C2 equals C1 XOR C3. Okay, how do I find what C2 is? What C1 and C3 are telling me about C2. So, wherever you have 2 and 3, you replace them with 1 and 3, you will get the Lx2. Okay. So, here you will have absolute value is f of absolute value of L1 plus f of absolute value of L3, and then sine of Lx2 is sine of L1 multiplied by sine of L3. Okay. And then let us just look at Lx3, which comes from C3 equals C1 XOR C2. Here again f of absolute value of L1 plus f of absolute value of L2, and then sine of Lx3 equals sine of L1 times sine of L2. Okay. So, this is how it works. So, there are 3 values to compute here, the soft outputs L1, L2 and L3, and you need this function f. Okay. Once again, let me remind you what this function f is. So, what is f of x? Well, let me remind you what f of x is. We defined this a little bit earlier. F of x is absolute value of log tan hyperbolic of absolute value of x by 2. Okay. So, this is f of x, and we use f of x in this decoder. So, now if you stare at it a bit more closely, you can do a little bit of a simplification here. Okay. So, you can compute all the 3 values in one interesting way. So, what you can do is you can find 2 values here. One is capital S, which is f of absolute value of L1 plus f of absolute value of L2 plus f of absolute value of L3. And then you can find a capital P here, which is sine of L1 times sine of L2 times sine of L3. Okay. and what is Lx1 is S minus f of L1, okay, times P times sine of L1. Okay, so convince yourself that that's true. This is the absolute value. I'm sorry, I think I missed f of, okay. Okay, it's f of S minus f of L1, and this is you can see this is the sign, right. What happened? P is the product of all the three signs. I am multiplying with sine of L1. So, this will become sine squared of L1, but sine squared of L1 is just 1. Okay. So, it will just be sine of L2 times sine of L3. Okay. So, likewise you can also find Lx2 is f of S minus f of L2 times P times sine of L2, and Lx3 is f of S minus f of L3 times P times sine of L3. Okay. So, this is the 3 extrinsic LLRs, and once you find the 3 extrinsic LLRs, you can simply add to the intrinsic LLR and you will get the total output LLR. Okay. So, this is the derivation of the SISO decoder for the single parity check code, and that brings us to the end of this lecture. What I will do in the next lecture is write some simple MATLAB code to illustrate how the repetition SISO decoder for the repetition code can be written down, how the SISO decoder for the single parity check code can be written down. We will see these are simple, relatively simple implementations, and then we will see some simplifications of the decoder. So, in fact, one of the things that is not very nice about this single parity check code decoder is this nonlinear function log tan hyperbolic. So, how do we get rid of that? Are there good approximations to get rid of that nonlinear function? Turns out the answer is yes. We will do that. We will do that in the next lecture. So, the next lecture will have some MATLAB coding along with a simplification for the SISO decoder for SPC. Thank you very much.